Okay, in this lecture, which is a two-part lecture, we're going to talk about a philosopher and historian of science named Thomas Kuhn and his important work on scientific revolutions. Even if you've never heard of Thomas Kuhn, you have probably come across his ideas as they were very influential in the past few decades. And this is going to set the stage for what we're talking about in the coming weeks, about all sorts of important topics like scientific consensus, when contrarians are genuine innovators in science versus when they're cranks or con men. Is scientific change rational? We're going to be looking at kind of the way the social structure of science impacts scientific progress, and just a bunch of related issues. And a lot of this stuff was kind of kicked into gear by Thomas Kuhn. And we'll also assess his ideas. He got some things right and he got some things wrong. So let's just get started. Again, Thomas Kuhn, he influenced a lot of positive developments in our understanding of the history of science and current scientific practice. But he also influenced a lot of skeptical and denialist attitudes towards science today as well. And his most famous book is this book, The Structure of Scientific Revolutions, which will be kind of exploring the ideas in this book and seeing what the implications were. So in this lecture, we're going to first look at the Pre-Kuhnian view of science, and this is probably a view of science that you were taught, in various science classes in high school and college. And it's a view of science that you find in a lot of science textbooks. Then we're going to look at a concept called paradigms, and which plays an important role in Thomas Kuhn's account of science. And then we're going to look at what Thomas Kuhn calls normal science, revolutionary science, and then we'll lastly look at his kind of controversial views and the impact of those views, and we'll assess them as well. But as I mentioned, some of this stuff is we're going to go returning back to this stuff in later lectures. So I'm not going to address every criticism of his views today. So here's the overview. Scientific ideas change all the time. Pick any scientific discipline, and it is practically guaranteed that it has widely different views than it did 50 or 100 years ago. As an example, let me tell you a story. In the 1800s, doctors thought that the primary cause of disease was imbalances in the 4 humours, which are blood, phlegm, black bile, and yellow bile. In fact, the humoral theory of disease was the dominant theory of disease for several thousand years. You find the Greek physician and philosopher Hippocrates articulating it, I believe, and then you find this in the medieval times, throughout much of the Renaissance, and again throughout a lot of the Enlightenment as well. So the most dominant humor and the most frequent culprit of imbalances was blood. That stuff coursing through your veins right now. So basically, when you have too much blood, you have an imbalance, and that might explain various diseases that you have or various maladies you're suffering from. So the treatment for an imbalance of excess blood was bloodletting, the literal draining of blood to restore balance. This is a very common practice for a long time. For thousands of years, up until the 1800s. Actually, up until the 1900s. In the early part of the 1900s, it was still a very common practice in most parts of the world, including the United States and most of Europe. Well, there was a Hungarian doctor, Ignaz Semmelweis, who was one of the scientists who challenged the humoral theory of disease, and then laid the groundwork for the now dominant theory of disease today, the germ theory of disease, which you are all familiar with. So Semmelweis was trying to solve a medical mystery. There were large numbers of mothers who were dying after giving birth in the doctor's ward in his hospital. But there was a different ward where women gave birth, the midwives' ward, and very few women died in the midwives' ward after giving birth. In fact, strikingly, the doctor's ward had 3 times as many deaths as the midwives' ward did. That's a lot. In fact, a woman was less likely to die if she gave birth in the street outside the hospital than if she gave birth in the doctor's ward. So this is a mystery. What's going on? Semmelweis noticed a pattern, though. Mothers were more likely to die after giving birth when the attending doctors in the doctor's ward had handled human corpses. And many of the doctors were handling human corpses. There was a morgue, there was also a medical school, there were students handling dead bodies. So they would handle these dead bodies, and then they'd go deliver a baby. But here's the kicker. They would not wash their hands first after handling the corpse and then delivering the baby. They would not wash their hands. Or they would wash their hands with like soap, but nothing, stronger than that. So Semmelweis implemented a hand washing policy where the doctors had to wash their hands with chlorine. And when he did that, the mortality rates of mothers in the doctor's ward dropped dramatically. One of the reasons he wanted to use chlorine was they noticed that, like, if you handled a dead body and then you wash your hands with soap, your hands still smelled like a corpse. Like, literally, your hands smelled like a dead body. But when they washed their hands, and your clothes would smell like a dead body if you washed them with soap. But if they washed their hands with chlorine, the smell of a dead body went away. By the way, just a lot of progress in medical science is gross. Just to be warned. But be glad, that it took some gross things to discover things that have improved your life today. Like the fact that now doctors wash their hands with strong bacteria and virus-killing soap. So Semmelweis' research, then, it was a very important step towards the eventual widespread and now consensus view of the germ theory of disease. This was developed further by Louis Pasteur. Semmelweis' research also was a very important impetus for the adoption of antiseptic procedures in surgery. Joseph Lister was also the person who kind of later gave this a major credibility boost. And antiseptic just means that surgeons, wash their hands and clean their tools before they cut you open and stick their hands inside your body. And again, isn't it nice that surgeons know to do this now? But here's the kicker. During Semmelweis' time, his research was actually shunned by the medical establishment because it conflicted with the dominant humoral imbalance theory of disease. Now, Semmelweis had kind of a combative personality as well, but he was actually eventually placed in an insane asylum, and tragically he died after a beating from the guards. You can read more about him on many places online and many medical history books, but his life ended tragically. So he was kind of at the time he was an outlier, he was contrarian, he had crazy ideas that conflicted with the consensus view of the medical establishment, and he was shunned and ostracized as a result and died a tragic death, probably in part because of that. Yet, in hindsight, now we know that Semmelweis was right, and the dominant consensus view of the medical establishment at the time was way off. In fact, very dangerously off. So, this leads back to a question then. So that was one episode of scientific change. Is there a pattern to the way science has changed over time? Are later theories always objectively better than earlier ones? Or are later theories objectively better at all? Is there is the germ theory of disease objectively better than the humoral imbalance theory of disease? My hunch is most of you would think yes. So some preliminaries before we look into Kuhn's main ideas. First, perceptual observation is not independent of theoretical beliefs. We learned this in the lecture on theory and observation. Depending on how you're primed, you'll see a young woman or an old lady, and it doesn't matter what you can't help but see the top line is longer than the bottom line, even though you actually know that both of these lines are actually identical in length. So again, your perception, your observation through the five senses is somehow mediated by various background beliefs that you have. There's no such thing as theoryless observation. There's also no general solution for distinguishing reliable from unreliable scientific claims. Whether a claim is reliable or not is going to be dependent on particular facts about that claim rather than some universal schema. We learned about this when we studied the problem of induction. So for, again, the reasons the germ theory of disease is better than the humoral theory of disease is different than the reasons that the heliocentrism, the idea that the Earth orbits the sun, is better than geocentrism, the idea that the sun orbits Earth, and it's also different from the reasons that it's better than flat Earthism. Thomas Kuhn challenged this view then. He's and his arguments persuaded a lot of intellectuals for a few decades, and his ideas have kind of trickled down to public discourse as well. Now, I'm not saying he was successful, but it's worth exploring his ideas because he was so influential. So, the Pre-Kuhnian view of science, again, this is a science that you learned in various science textbooks in high school, has several kind of components. First, we assume that science is objective. It's not settled by subjective preferences. The reason we prefer the germ theory of disease to the humoral theory of disease is we think that the germ theory of disease is better supported by facts. It's not because we agree with the political views of people who endorse the germ theory of disease, for example. Second, we assume that science is a paradigmatically rational activity. It's the surest route to truth. Using scientific methods and techniques is the best way to arrive at true beliefs, and the best way to weed out false beliefs. We also assume that science progresses cumulatively. We assume that by the application of an unchanging scientific method, new ideas are accepted on the basis of good evidence. And we think that science progresses by adding to the store of pre-existing facts. Here's an example. Early fact was that, we discovered that unwashed hands cause disease. This is what Semmelweis discovered. So, we progressed. Maybe these invisible things called germs cause disease. And perhaps there are germs on your unwashed hands. Later, as we improved our investigative techniques, we learned that viruses and bacteria cause disease. So germs are viruses or bacteria, and those cause disease. And now we know in 2021, or whatever year you're watching this lecture, that sucking on doorknobs can cause E. coli infection. Which is why if you're going to suck on a doorknob, make sure you sanitize it first. But in general, I don't recommend doing that. Okay, another pre-Kuhnian view of science is that science is a story of heroes and villains. And the villains dogmatically hold on to old ideas that conflict with the evidence. So Aristotelians thought that the Earth was the center of the universe. Creationists didn't believe in evolution by natural selection. Doctors back in the day thought that humoral imbalances were the cause of disease, and bloodletting was a cure, rather than, germs and hand washing. And then the heroes were the, people who bravely followed the evidence wherever it led, in spite of the consequences, like Galileo and Darwin. Remember, Galileo turned out to be right. The Earth is not the center of the universe. Instead, the Earth orbits the sun. But Galileo spent the last few years of his life under house arrest because his views conflicted with the mainstream opinion at the time. And again, Ignaz Semmelweis, the guy who had the crazy idea that doctors should wash their hands before they deliver babies, was shunned by the scientific community and died in an insane asylum. Another pre-Kuhnian view of science is a very important distinction that I'm going to explain between the context of discovery and the context of justification. So the context of discovery is a historical process by which a scientist arrives at a theory. It is subjective and psychological. It's a subjective and psychological process. Oftentimes it's just due to luck. So I'll explain what this is through examples. In 1865, the German chemist Kekulé discovered the hexagonal structure of a benzene molecules because he had a dream of a snake biting his own tail. Now dreaming that a snake bites its tail isn't, rational evidence for the structure of a molecule, but it gave him an idea that led to the actual discovery of the shape of the molecule. It was the rational justification, more sophisticated laboratory techniques. So again, sometimes you don't discover important scientific ideas by rational means. Example from pop culture. In Back to the Future, Doc got his vision of the flux capacitor after hitting his head while falling off his toilet after he was trying to hang a clock. Again, some of Einstein's most important ideas about the special theory of relativity just came from him daydreaming about riding a light beam. Okay. Again, that's not rational justification for the special theory of relativity, but it kind of was like planted the seed. So this is distinguished, though, from the context of justification. The context of discovery is not the same thing as the context of justification. imagining riding a light beam doesn't justify special theory of relativity. Imagining a snake biting its tail doesn't prove or confirm the structure of a benzene molecule. So the context of justification is how scientists rationally justify a theory. That's through tests, through finding the appropriate evidence, comparing it with rival claims. This is objective. It's a matter of logic. It's not due to luck. It's lucky that Kukuli dreamed about a snake biting its tail. Okay, it was luck that Doc hit his head and saw the flux capacitor in a vision. But that wasn't the context of justification. All right, so in the Pre-Kuhnian view, and you learn this in science textbooks as well, is that the context of justification is what matters. How a theory is rationally justified is more important than how it is discovered. Okay, it's more important. Another Pre-Kuhnian view of science, and again, actually going back to this real quick, Kuhn kind of challenges this. He thinks, like, no, there's a lot more to the context of discovery, to the irrational factors. There's a lot of scientific changes explained by these irrational factors, and we're going to return to that point. But another point is that theories, in the Pre-Kuhnian view, are distinct from observational facts. And I won't spend a lot of time on this because we spent the whole lecture on it. But so on the, what you learn in science textbooks is that when you have different theories that make rival claims, you can figure out which theory is better by comparing the theory with neutral observational facts that all parties accept. And in fact, the rationality and objectivity of science depends on a clear distinction between theories and observational facts. Thomas Kuhn, again, challenges a lot of this stuff in his work. He wants to focus more on the history and sociology of science, what you could say is the human side of science. After all, scientists are humans. They have biases and superstitions just like everyone else does. Quick question. What's a scientific theory? You can press pause and think, and then I'll answer it for you. Okay, here's the answer. It's just a bunch of sentences. Literally, a scientific theory is a bunch of sentences conjoined together. Some theories have a few sentences, some theories have a lot of sentences, but they're just a bunch of sentences. Here's another thing about theories. Some sentences are true and some are false. In just about any scientific theory, it will have true sentences and false sentences. Well, Thomas Kuhn argued that you cannot separate irrational biases from properly scientific attitudes such that all the true sentences in a scientific theory are explained by rational scientific attitudes, whereas all the false sentences in a theory are explained by irrational biases, maybe from the reptilian part of our brain. So we think, here's a theory, it's got true and false sentences. Well, the true sentences were explained by, using proper scientific methods, and the false sentences, which will eventually be weeded out and replaced by true sentences, are explained by irrational factors. Kuhn says, no, that's not how it works. In fact, even when older theories have true scientific beliefs as components, according to Kuhn, it does not follow that the true beliefs were arrived at correctly by applying a universal, unchanging scientific method. Furthermore, the methods themselves are subject to debate. Kuhn was especially interested in scientific revolutions. These are periods of great upheaval where existing ideas are replaced with radical new ones. For example, the Copernican revolution, or Einstein's theory of relativity, or Darwinism, or I don't have this on the slide, but when the germ theory of disease replaced the humoral imbalance theory of disease. Scientific revolutions, though, of course, are extremely rare. So Kuhn was also interested in what he called normal science. This is the ordinary, mundane, day-to-day scientific activities when science is not undergoing a revolutionary change. So Thomas Kuhn had several features of his positive account of scientific change. One, we have to see just what he means by what a paradigm is. And then we have to look at what he has to say about normal science. And then we'll look at what he has to say about scientific revolutions. So paradigms have two components. There's a set of core theoretical assumptions that all members of the scientific community accept, like what exists, For example, maybe electrons and protons and neutrons, or electrons and quarks. What properties do things have? So, for example, subatomic particles have charge. How do they interact, including with our senses? Opposite charges repel. Opposite charges attract. Identical charges repel. And then you have a set of exemplars, or particular scientific problems that have been solved by means of these theoretical assumptions. So, for example, we're able to explain a lot of the different types of elements based on the properties of subatomic particles, and also features like the orbits, how many electrons they can have in their orbits to make them stable or not. So, important, a paradigm is not just a theory, okay? A paradigm is not just a theory. It's not just a bunch of sentences. Instead, when scientists share a paradigm, they agree on how future research in the field should proceed, which problems are the pertinent ones to tackle, what is the appropriate method for solving problems, and what acceptable solutions to problems look like. So a paradigm then is more like an entire scientific outlook. It's a bunch of shared assumptions, beliefs, and values that unite a scientific community and allow what can cause normal science to take place. It tells the community what is good and bad science. And so it's kind of like, it's a whole way of looking at the world, basically. It's a whole way of seeing the world and experiencing the world. And this is plausible. Remember the lecture on theory and observation, or how theoretical beliefs influence how you literally observe the world. So a paradigm is, includes that. And so it can explain a lot. Now, the history of science is best understood as a succession of paradigms. You have one paradigm replacing another. So in most scientific fields, there is a time when there was no generally accepted scientific theory, but something resembling a scientific investigation occurring. For example, in the history of optics, there was no one dominant theory of light until Newtonian optics. And then while all scientists might be interested in the same topic, they have different core commitments. So they will regard different aspects as more important than others. They'll have different disagreements about the methods that should be used or the questions being asked. There's generally no consensus, okay, during pre-paradigm science. No consensus. And as we noted in the lecture on philosophy and science, a lot of pre-paradigm science originates from philosophy, questions that philosophers ask. So normal science emerges from a major and exemplary scientific breakthrough, which then becomes a model that defines the future practice and direction of that science. For example, some of Louis Pasteur's experiments showing that spontaneous generation does not occur was kind of like, the major achievements that led to the germ theory of disease eventually becoming the consensus view in the medical community. So in normal science, the theory is especially successful at explaining certain types of phenomena and has the promise to explain further phenomena. So it doesn't explain everything, but it's got the potential to explain a lot. So like Darwinism was able to explain the variation you see amongst different species. Mendel's work could explain inheritance. Einstein's general theory of relativity could explain gravity. And of course, the germ theory of disease can explain all sorts of diseases. And how to treat them as well. And in normal science, there's a universally accepted paradigm that is accepted in a community of scientists. And this paradigm determines what questions are worth asking, what problems are worth solving, and what methods you would use to solve those problems. And students are kind of taught the practices and assumptions of the scientific community in their scientific education. So a lot of scientific education is a way of learning how to see the world through the paradigm. And this is true. If you're a science major, whether it's economics or psychology or chemistry or biology or whatever, you're being trained in that paradigm. And we learned about this in the lecture on theory and observation as well. Like, different, you're literally learning how to see things that you couldn't see before. For example, an oncologist can see tumors in an X-ray that a scientific layperson could not see. So during periods of normal science, it's actually difficult to imagine alternative ways of doing science. You don't challenge the core ideas. So like, no astronomy professors aren't going to say, maybe the Earth is flat. During normal science, the facts are investigated with more and more precision. Successful views are exported to related inquiries. So we see this now. Should we use neuroscience to study economics? Should we use evolutionary theory to study psychology? And during this, during the transition to normal science, that's when science becomes professionalized. That's where you get the journals and various academic departments, and you get various societies. Oftentimes, the concerns of normal science are narrow, and the value of what scientists are doing this aren't going to be obvious to the general public. In fact, a lot of criticism of science you find in the public sphere is oftentimes based on a misunderstanding of the importance of what the scientists are working on. So let me tell you another story. Let me tell you the story about the allegedly $3 million shrimp treadmill. So in 2011, Oklahoma Senator Tom Coburn wrote a report criticizing wasteful government spending. And an example of such wasteful spending was a shrimp treadmill. So what was this shrimp treadmill? The biology professor at Pacific University, Professor David Shulnick, was one of the researchers who developed and invented this kind of shrimp treadmill. And yes, here's an actual shrimp on the treadmill. So the rumor mill got started. There were a lot of articles criticizing this, and you heard varying figures tossed about. Some said it was $500,000. Some news reports, and said it was $3 million. This is. I mean, it's true. It's ridiculous. A $3 million shrimp treadmill. What are these researchers doing with the money that they're being given by government grants? Here's what was actually going on. So the shrimp treadmill was used to investigate how changes in the marine environment would impact the ability of crustaceans to fight bacteria. And it's important to know this because, for one thing, the oceanic environment is changing for a variety of reasons, most prominent climate change. And also, much of the marine ecosystem depends on crustaceans. Shrimp are very important. They eat a lot of the algae, and then they're also the food for a lot of other important animals in the oceanic ecosystem, not to mention the seafood industry. So it's important to understand how changes in the marine environment would impact shrimp behavior. As an aside, the treadmill actually only cost $50, something that was lost in some of these rumors. So this is an example, though, of like a very narrow concern in scientific research, where the value isn't obvious to the public. But, to someone trained in this stuff, it's, they can see the value of it, and they can see the importance of it and where it fits everything else. So a lot of normal science is like this. It's like, to the outsider, it's esoteric. But to the insider, they could see the value of it. And oftentimes it takes a lot of training to appreciate the value of various studies that researchers are doing. So going back to normal science then, successful paradigms will eventually encounter problems. They'll encounter phenomena that the paradigm can't accommodate. There might be mismatches between the theory's predictions and experimental facts. Usually these are puzzles for the practitioners to solve, though. So these aren't fatal, devastating problems, usually. In fact, there's an analogy with crossword puzzles. With crossword puzzles, there's a clear way to solve it, and there are inappropriate ways to solve it. And scientific puzzles in normal science are like that as well. We don't know the answer, but there is a clear way to find out the answer. There's just a clear way to solve this. So then the job of a normal scientist is basically to eliminate these minor puzzles while making as few changes as possible to the major overall paradigm. So normal science is generally a very conservative activity. Medical researchers aren't going to try to challenge the germ theory of disease. Astronomers aren't going to try to challenge heliocentrism. Physicists aren't going to try to challenge, special theory of relativity. So normal science then usually it develops and extends an existing paradigm. It makes it more accurate and precise, but it's successful when it's not finding novelties that challenge the paradigm. And when they do, they quickly want to find ways to figure it out. So I've mentioned this before, but a couple years ago there was an article saying that allegedly physicists had discovered a particle that is faster than the speed of light, which violates the core postulate of the special theory of relativity, that nothing is faster than the speed of light. And eventually they were to find out that nope, turns out they're wrong. There aren't particles that are faster than the speed of light. So importantly, in normal science, scientists are not trying to test the paradigm, okay? They're not trying to test it. And generally in normal science, the paradigm is immune from criticism. Instead, scientists accept the paradigm unquestioningly and conduct their research within the limits set by the paradigm. And when experimental results do conflict with the paradigm, the scientists don't assume that the paradigm is faulty. They assume that the experimental setup was faulty. Something is wrong with the equipment, for example. So, eventually though, there was a bunch of things called anomalies pile up. So what are anomalies? Anomalies are problems that the paradigm does not clearly solve. And in normal science, the anomalies are dealt with in an ad hoc manner, on a case-by-case basis. There's no one general formula to deal with anomalies, basically. So sometimes scientists will tweak the paradigm. Sometimes they'll just say that, hey, the anomalies aren't significant. Sometimes they'll say, well, they actually don't exist. They'll just dispute the existence of the anomalies. In fact, most normal science, most scientific textbooks don't really bring up the anomalies. They treat the paradigm as unproblematic. No one's going to question the periodic table of elements in a chemistry textbook, or Newton's laws, like for example, at force equals mass times acceleration, or Mendel's laws of inheritance, for example. But over time, in normal science, anomalies are discovered that cannot be reconciled with the paradigm. Some are solved, some are ignored, but eventually they accumulate and big ones remain unresolved. And then a sense of crisis takes over the scientific community. Their confidence in the paradigm breaks down. Normal science grinds to a halt. Here's a strained analogy. Normal science is like a snowball, and eventually it accumulates so many anomalies that it just topples over. So this leads to a crisis state. A crisis state is the beginning of the process of revolutionary science. Core working assumptions are viewed as mistaken. Various fundamental scientific ideas are up for grabs, and a variety of alternatives are proposed. When a science is in a crisis state, a bunch of paradigms compete, and no paradigm is universally accepted. Instead, rival paradigms are introduced by rebel bands of scientists. Oftentimes, these are scientists who are new to the field, and they're able to see the world in a different way because they're not been, spectacled by the old paradigm. They haven't been influenced by it. Like Einstein made his biggest discoveries when he was like a man in his early 20s working as a patent clerk. The new scientists then are often ostracized and they're criticized by the main body of scientists. They're, for example, accused of not practicing good science or not practicing science at all. They're accused of engaging in unjustified speculation. But nonetheless, the existence of new groups of scientists is crucial for major episodes of scientific change. Now, I note, and I'm not going to do that in this lecture, but I'm going to be doing this in future lectures in the upcoming weeks. An important skill is distinguishing between scientists who are genuine innovators, like the Einsteins and the Galileos and the Semmelweises, from cranks or deniers or contrarians or con artists, okay? Because oftentimes cranks, deniers, and contrarians claim that they're the innovators. So, Galileo, Einstein, Darwin, Semmelweis, they're genuine innovators. Some of these fellows are not, but they claim to be. The guy at the top is Andrew Wakefield, and he was the guy who claimed that the MMR vaccine causes autism, and he was exposed to be a fraud. More about that in later lectures. And then the two bottom fellows, Fred Singer and Fred Seitz, were climate change deniers and a bunch of deniers of a bunch of acid rain pollution deniers, ozone hole deniers. So you need to learn how, for the scientific layperson, though, it's not always obvious. Is this a genuine innovator or is this, a crank? And we'll be talking about how to distinguish between these two in later weeks. Anyways, back to crisis science, though. Eventually, thanks to a major scientific achievement, a new paradigm is established, and this, according to Kuhn, is a scientific revolution. Einstein's stuff, Newton's stuff, Darwin's discoveries in the Galapagos Islands, the discovery that, Louis Pasteur's, well, I'll get into that. So there are two necessary conditions for a scientific revolution. One is the crisis state, which we already looked at. And then two, there's got to be a new exemplar. There's got to be a major scientific achievement that has a blend of success and promise. And important, scientists won't abandon a paradigm, no matter how many problems it has, until there's a new and promising exemplar that hasn't had a major success. If there's nothing to replace a paradigm with, they're probably not going to abandon it. Okay? So you don't get rid of Newtonian gravity until you get Einstein's general theory of relativity's explanation of gravity. Okay? And a major scientific success was his accurately predicting the deflection of the sun's rays during an eclipse, for example. Why? Why won't scientists abandon the paradigm until there's a promising new success? It's because, again, paradigms provide guidance on what to investigate and how to investigate it. They have to have some sort of framework to work with. So, according to Kuhn, and this is probably historically accurate, a generation is usually required before a scientific community is won over to a new paradigm. The old guard usually needs to die or retire. In fact, with Copernicanism, that was the case. So Galileo was placed under house arrest for defending the idea that the Earth orbits the sun. Several other famous thinkers like René Descartes published a book also assuming the same view, but he didn't let it get published until after he died because he was scared of also getting arrested. But within 100 years of Galileo's and Copernicus' time, the reviews were dominant. They're accepted in universities. No one taught that the Earth was the center of the universe anymore. So it was in a very, very short time span. So the scientific revolution occurs then when the new paradigm defeats its rivals, and it becomes universally accepted. And then you get a new period of normal science, with new rules, new methods, new standards, new puzzles, new questions, and new solutions. Another important point is, in a scientific revolution, according to Thomas Kuhn, the replacement of the old paradigm with a new one is not a gradual, piecemeal process. It's a sudden, complete replacement. The new paradigm completely replaces the old one. The new paradigm may retain some of the old terms, but they have very different meanings. For example, mass means something very different in Einstein's theories versus Newton's theories. Also important, in the history of science, according to Kuhn, the history of science, according to Kuhn, is not new theories, simply refining old ones and preserving old theories as limit cases, moving cumulatively to a truer and truer picture of the world. Instead, it's a bunch of jerky replacements. No, not beef jerky. Basically, the old theories are completely abandoned. The new ones are completely embraced. And according to Kuhn, the same thing will happen to our current theories. So according to Thomas Kuhn, then the history of science warns us against believing present theories. If he's right, then you should not believe the germ theory of disease. You should not believe in evolution. You should not believe that the Earth is orbiting the sun if Kuhn is right. Seems counterintuitive. More on that later. But according to Kuhn, we usually assume scientists adopt a new theory in place of old ones on the basis of evidence. But according to Kuhn, it's actually an act of faith. According to Thomas Kuhn, reasons alone could never rationally compel a paradigm shift. Instead, scientists adopt new paradigms thanks to peer pressure. And that, according to Thomas Kuhn, explains the paradigm's rapid acceptance in the scientific community. And again, I'm going to be looking at more about this in the coming weeks. So if Kuhn is right, though, paradigm shifts and scientific revolutions are not rational. The replacement of the humoral theory of disease with the germ theory of disease was not rational if Thomas Kuhn is right. But don't scientists rationally assess two competing paradigms and choose one over the other on the basis of its evidence? Again, according to Thomas Kuhn, the answer is no. According to Kuhn, the view that science progresses toward truth in a linear fashion, with old incorrect ideas replaced by new correct ones, and later theories being objectively better than old ones, is historically inaccurate and philosophically naive. Why? Kuhn gives two reasons, which we'll look at. What he called the incommensurability thesis, and then the idea of the theory-ladenness of our observations in language. So let's talk about incommensurability first. So paradigms determine a scientist's worldview. When you're replacing one paradigm with another paradigm means adopting a whole new conceptual framework to make sense of the world. So two paradigms then are completely different worldviews. So straightforward comparisons are impossible. There's no common language which both can be translated. Okay, I mean, we can translate from German to English. It's raining. Es regnet, but it's apparently, according to Kuhn, you can't do that with like the language of different paradigms in science. Well, why does Kuhn argue this? Well, according to Kuhn, scientific concepts derive their meaning from the theory they play a role in. Mass means something very different in Newton's theory than in Einstein's theory. So according to Thomas Kuhn, Newton and Einstein are speaking different languages. Okay. So given the incommensurability thesis, according to Thomas Kuhn, theory comparison is impossible. Theory comparison requires a common language, but according to Kuhn, there is no common language. Proponents of new and old paradigms are literally talking past each other. Scientific standards are also incommensurable. People who are proponents of different scientific paradigms disagree about what features a good paradigm should have, what problems it should solve, what acceptable solutions look like. According to Thomas Kuhn, it's like arguing about fashion, okay? And it's not like, one fashion's rationally better than another. It's just different tastes, different subjective preferences, okay? So Ron likes one style of jorts. Tom likes a different style of jorts, the cutoffs. Why is one better than the other? It's just subjective preferences. It's just mere taste. Kuhn says that theory choice in science is like that. So incommensurability then challenges also the linear view of scientific progress. The idea that science has just progressively added more true beliefs and replaced false beliefs with true beliefs in a kind of towards, a truer and truer accurate picture of the world. But according to Thomas Kuhn, if paradigms are incommensurable, then it is wrong to think of revolutions consisting of right ideas replacing wrong ones. So calling one idea right and the other wrong requires a common framework. But given the incommensurability of paradigms, there is no common framework. So if Kuhn is right, scientific change is directionless. It is not for the better or for the worse, which seems counterintuitive. Isn't the germ theory of disease better than the old humoral imbalance theory of disease? Well, if Kuhn is right, the answer is no. Well, let's also take a look at the other reason Kuhn thought that scientific change was irrational, an irrational process. And it has to do with the idea of the theory-ladenness of science, of both our observations and our language. So when you're comparing two theories, according to Kuhn, so in the old view, when you're comparing two theories, scientists can appeal to neutral facts to decide between them. But according to Kuhn, all data is contaminated by theoretical assumptions, so there are no neutral facts to appeal to. Why? Well, one reason is that there's no theoryless observation. As we've already seen, our perception is conditioned by our background theoretical beliefs. So what we see depends in part on what we believe. Also, there's no theory-neutral terms. Scientists' experimental and observational reports are in very theoretical language. Here's a simple sentence: the electric current flows through the copper. All of these terms are very theoretically loaded terms, okay? So, what are the consequences of theory-ladenness? First, according to Kuhn, disputes between competing paradigms cannot be resolved by appealing to neutral data because there is no neutral data. What counts as data or facts instead depends on the paradigm. A perfectly objective choice then between two paradigms is impossible because there is no neutral vantage point. Second, there is no objective truth. To be objectively true, a theory must correspond to neutral facts, but facts are infected by theories, so there are no neutral facts. Instead, according to Thomas Kuhn, what is true is going to be merely relative to a paradigm. So according to one paradigm, the germs are the causes of diseases. According to another paradigm, humoral imbalances cause diseases. So there's no rational way then to compare paradigms, because there's no common measure by which to assess the paradigms. There's nothing outside the paradigms that could be a common ground. Different theories equivocate on the meanings of the terms they employ. In fact, the very criteria themselves for comparing competing theories are dependent on a paradigm. So, what's rational for one theory is not rational for another. As I already mentioned, rationality itself is paradigm relative. It's relativism. Why? Well, according to Thomas Kuhn, a paradigm shift is basically a Gestalt switch. Okay, when you change from one paradigm to another, it's immediate. It completely replaces one way of seeing the world with another. So take a look at this. You can see a rabbit or a duck, but you don't gradually shift from seeing a rabbit or a duck piecemeal, in a gradual process. It's all at once. Now I see a duck, now I see a rabbit. That's how scientific change occurs. That's how a paradigm shift occurs, that is, according to Kuhn. Just all at once. Theory choices are the same. They happen all at once. First you see the sun orbiting the Earth. Now you see the Earth orbiting the sun. By the way, who is that? Oh, it's my Uncle Frank again. All right, stay tuned for part 2.